So the point is that this spectrum, for instance, I have an example there. Say this is the energy to the 0 point of the cavity. Say in the Mott insulator phase, something like particle and Hall spectrum, with a gap which tends to 0 when you approach the transition to the superfluid phase. While on the superfluid phase, you have something which has the usual form with a diffusive branch. And this was calculated from Gutzwiller ansatz, factorizing sites, and then doing the linearization. I have no idea if this is a correct procedure. Some more sophisticated calculations are definitely necessary. Dynamical mean field theory could be one, or exact diagonalization, anything to understand what's happening. The point that is important to make, even if the details are a bit changed, is that all these modes are optically accessible. So if one does a pump and probe on this system, these branches should appear as peaks in the response, like Bramati has done for the diffusive mode in the superfluid state. So this is interesting to investigate and compare to the theory, also to understand whether Gutzwiller is fine or whatever has to be done.
And you make the statements for 8 sites, right?
Sorry?
You are making the statements for 8 sites.
No, this calculation is done in the thermodynamic limit. It's large system.
I just want to make sure, that's all.
Yeah. Numerics are for, we got to 10, but I think people which are good in numerics could do 3 times more, but we are beginners in that.
So any more questions? For now, yeah.
So just generally, by the fact that the system is open and there is a pumped and dissipative, does this put some a priori limit to the category of many body states that you will be able to do or not? It could be, the important thing is just to find some degrees of freedom that are decoupled somehow, and then you can go as far as you want in constructing many body states.
I think the variety of states one can create is huge, and perhaps even larger than the one of the low energy states of standard equilibrium systems. I think there are ways to find the new states. I don't exclude that. At the same time, you have the quantum fluctuations that come back into the system because of driving and dissipation, give a sort of temperature to the system between triple quotation marks, which somehow make the system more fragile towards thermal effects. So if the system is extremely fragile against temperature, I guess you may be in trouble, unless you have some gap protecting you. Because then if you have a many-body gap, you may be safe, because this protects you. Just to give you an example, Bramati's experiment on the superfluid light, these, if you do the calculation beyond the mean field, doing just Bogolyubov, you calculate the steady state at Bogolyubov level, you have a temperature between triple quotation marks around mu, around the interaction energy. And there is no way of going below. And this basically comes from this process. You have a Bogolyubov dispersion. You lose one particle because your system can emit particles. If you lose one particle, in the Bogolyubov basis, you can either lose a Bogolyubov particle, U, or create a Bogolyubov particle via VV. So if you expand the particle loss in the Bogolyubov basis, is a B plus B DAG. The fact that you can create Bogolyubov excitations means that losses are heating the system. They are heating the system to an energy which is typically the interaction energy. What in condensates would be mu. This is often not a problem. For Alberto, it has never been a problem. But it would be a problem if you try to use these quantum fluids of light for analog models of gravity, to see Hawking. To see, say, processes like analog Hawking emission, where having some temperature would spoil the typical quantum correlations which are present in the process. Because the system is not at 0 temperature. So this is a bit double phase. It's not yet understood yet. I think there are plenty of questions. That's why we need to really build a theory, do more experiments, and understand things in a deeper way.
Okay, so then we should then stop and come back for the discussion session, and then thank you, the speakers.